Welcome back. Today we're going to start with a very important topic, that is electric potential. The understanding of the electrostatics or any inverse scale conservative kind of force would be incomplete if one does not understand fully the concept of electric potential. I rate this topic very high as far as the problem solving abilities of students are concerned. Rather, the numericals based on electric potential are easier than the numerical potential than the numericals based on electric field, simply because potential is a scalar quantity and you don't have to go into vector calculus, so mathematically that becomes easier to solve. Still, they are more important than the numericals on the field. And then obviously in the next lecture I'll do a few numericals which will be based on the combination of these two things, that's field and potential, both to be calculated. But for the time being, let's understand what the electric potential is. Electric potential, just like you studied gravitational potential, it's very similar thing. Basically, it's for, let's say some charge is over there and you wish to find out electric potential of point P at some distance r. What you need to do, you need to take a unit positive test charge Q naught, which is equal to 1 unit positive test charge. Take it from infinity and bring it slowly to this point P, and the total amount of work which you have done in doing so is electric potential of this point P. So basically, electric potential is defined as the amount of work done in bringing a unit positive test charge from infinity to the given point. There is one assumption in this. We are assuming potential to be zero at infinite distances, which is okay to be considered simply because it's an inverse scale law. So at r, as r approaches infinity, it is okay to consider that the total energy is zero, because we'll have to take some point as reference. That's why the infinite distance separation has been taken as a zero potential reference. Now, as you take this charge slowly towards this point P, I'm emphasizing again and again that slowly, it should be brought slowly towards point P, because we don't want this charge Q naught to get any kinetic energy. If it gets some kinetic energy, that means whatever work you have done was not only to bring this charge to point P, but you were also working to provide kinetic energy to the particle. So we are assuming that we bring it so slow that at any point its velocity, its speed and its kinetic energy are infinitesimally small, practically zero. At every point it was almost at rest. Now that can be a paradoxical situation. If it was at rest, how I am bringing it forward, but that's okay to consider when we are considering the steps to be infinitesimally small. I hope you remember the what we call as sand pile experiment, thermodynamics, when you put one grain of sand on the piston and the piston get depressed. Now that's so slow that the process can be assumed to be reversible and almost stationary, static. So similar kind of things that we are assuming over here. I recap what I have said till now. I don't know what electric potential is. We'll understand its significance later on. First of all, I'm just mathematically trying to find out the expression for electric potential. What is electric potential? The definition says it is the amount of work done in bringing a unit positive test charge from infinity to the given point at infinitesimally slow rate. So slow that practically it was at rest at all times. Now, during its journey, let's say the charge Q naught was at some distance x away from the point from the given charge q. Let's say I moved it further through a small distance dx. Since I'm assuming both of them to be positive, just for the sake of an example without loss of any generality, there will be some force acting on it in this direction. Now, force and displacement are at 180 degrees. So, small work done in displacing it through small distance dx, dw, would be given as f dot dx, which is equal to minus f dx, because cos 180 is minus 1. So, total work done, which would be called electric potential, what it is equal to? Work done is equal to integration f dx negative forces 1 by 4 pi epsilon naught q and q naught divided by x square and dx. Since it is work done per unit test charge, you won't mind if I divide both sides by q naught. So electric potential, now I am getting something concrete. Electric potential, which we generally denote with capital V, is equal to work done per unit test charge, and that is equal to 1 by 4 pi epsilon naught q 1 by x square dx. From where you picked up charge q naught? From infinity. And where do you want it to be placed finally? At a distance r. So the limits of integration are from infinity to r. So potential V is given as q by 4 pi epsilon naught integration x raised to power minus 2 dx from infinity to r. You know how to solve it out. V is equal to q by 4 pi epsilon naught. Integration is x raised to power minus 1 over minus 1 from infinity to r. I forgot this negative sign over here, so you won't mind if I put it over there again. Now this negative and this negative get cancelled out. What expression for potential we are getting? Q by 4 pi epsilon naught 1 by x from infinity to r. V is equal to q by 4 pi epsilon naught 1 by r minus 1 by infinity. 1 by infinity is 0. When one thing is to be distributed among infinite number of people, obviously you will get 0 thing per head. So potential, expression for potential is V is equal to 1 by 4 pi epsilon naught Q by R. Now this is a mathematical expression for electric potential due to a point charge at a distance r from it. Since it is work done per unit charge, work done is a scalar quantity, potential is a scalar quantity. Its units are work done per unit charge, so units are joule per coulomb. Now, in case of had there been a negative charge over minus q over here, the force would have been attractive and displacement would have been in the same direction. F and dx would have been in the same direction. This negative sign would not have been there. In that case, we would get it over there b as minus 1 by 4 pi epsilon naught q by r. The bottom line is, you don't have to use two disapparated expressions, but simply put q with its sign whenever you want to use this formula. With its sign implies if charge is minus 3 coulomb, write down minus 3 coulomb. If charge is plus 3 coulomb, write down plus 3 coulomb. So you are to use charge, the value of the charge, along with its sign while using this formula. I'll come to the nature of electric forces, the line integral of electric field, which turns out to be electric potential, and we'll prove that electric forces are conservative in nature using the concept of potential in the coming lectures. Thank you.